to kick that off, let me see if I can. To kick that off, it's my pleasure to have Stephen Elliott. He's IBM VP of the Chief Data Office to share with us his thoughts on the ONNX adoption into use cases inside IBM. So over to you, Stephen.
Awesome. Thanks, Thomas. Since I joined IBM 3 years ago, we've gone through numerous changes. I can tell you in the early beginnings of this, we're talking in developing a common tensor format, and we jumped on the ONNX bandwagon really, really quickly. I had discussions far before ONNX formation with many of the companies, the founders, Facebook, Microsoft, Amazon, and it was such a wonderful, experience to jump on that. And now, we have the Linux Foundation involved, and it's just, even brighter days ahead. And this has definitely made, what we have internally so much better than what we could ever envision. So today within IBM, we have pretty wide adoption within the company. We're always trying to push it further though. And it's a challenge that we have, certain obstacles and such, but I'm going to talk a little bit later about, how potentially the community can help us. But we have wide support in Watson machine learning to power systems and all the way down to our IBM Z system mainframes. Now, there's a number of important focus groups within the ONNX community, from Edge, Inference, and one that I love and is close to my heart, Training, and more. But for wider internal adoption within the IBM company and abroad, it's really around the ONNX machine learning initiative, ONNX ML. And it's by far the most important to myself at this point to kind of push the wide adoption of ONNX. And it's really just, a use case driven approach from our clients. Our clients are demanding it, and the use cases are heavily weighted towards non-deep learning methods and providing, broader functional support in ONNX machine learning would ensure, basically the triple crown for ONNX within IBM, and I think, the broader community. Now, ONNX, a little bit, diving in, I can't give specific stories and such, but I can tell you that has enabled our clients to train deep learning models in the modality of their choice, which is kind of the foundation statements of why ONNX exists, and effectively use the data where they want to. They could train in Watson, train elsewhere, and provide inference on the mainframe, or, on their power systems, or on x86, whatever it would be. And the scoring's got to be close to the data. And some of these are transactional based systems, it's got to be close to the data. And this has absolutely enabled those clients. And that we are appreciative to the community for, because like I said, it would have been, much more difficult to kind of go down those paths alone. So my hat is tipped right now. And those who know me typically will see me in a hat. I don't have much hair, so I typically wear that hat. And I definitely tip my hat to the community. We really appreciate all the open collaboration. I think we have, 130 some participants right now. Without you, it would have been a very, very difficult road. And again, I'd like to just thank the internal IBM groups, the open source group, all of those contributing down through research to those enabling this within mainframe everywhere. Thank you so much for the help on this. And if you have any questions, I'd open it up right now if you want to know what we're doing within IBM, or just send me an email thereafter. But that's the basis of it. We're trying to adopt it and use it more. And it's really, if we could hit the machine learning umbrella more generally, that would really enable us. And that's about it, Thomas. Thank you.
Yeah, thank you, Steve. All right. I think we're doing good on time, so let us keep going. Let me move to Zpeng. Let me stop share and find.
Do you want me to share?
Yeah, if you have the slide ready. Yeah.
Okay, sure. Can you see my screen now?
Perfect.
Okay. Perfect. Hello, everyone. I'm Howard from Huawei. We actually work with Microsoft hosted the very first ONNX China workshop 2 years ago, and we also participate in the second one last year. And really glad to be here in the third consecutive years. Hopefully, we'll have another, whether it's online or face-to-face workshop again, Q4 this year. So our team and also Huawei has always been a big believer in ONNX from the beginning, and we are also very exciting to see ONNX into LFAI. Okay, so today I'm going to talk about Myspare and ONNX. So Myspare is a new open source deep learning framework from Huawei. We just open sourced it, I think, less than 2 weeks ago. It's licensed under Apache 2.0, and you can check out our code from either Git or we have a mirror at GitHub. So Myspare is a new framework that designed to be used for mobile, edge, and cloud scenarios, and also highly optimized for Huawei's Ascend AI processor. So this is a really high-level overview of the general framework architecture. So as you can see, we have a Python front end enabling developer to write a graph, and we have a Myspare IR. Basically, we provide source code based like auto differentiation, and also we provide Ascend powered auto parallel. Basically, you add one line into your serialized code, and it will help you automatically run parallel jobs on a huge cluster. So currently, you can run the Myspare model on either on the cloud, on CPU, GPU, or with Ascend 910, and also on the edge with Ascend 310 or on your mobile phone. So we are hugely inspired by ONNX governance model. So we also set up a technical steering committee, which composed of 14 delegates across the globe. And also we have special interest group and working groups all modeled after ONNX governance. So we are slowly but gradually starting to creating the SIGs and help them to start to run open meetings and open development. And we have various community partners. Hopefully I will submit a request for the ONNX logo to be added to our webpage. As you can see, like DJI Lab is also like our open source partner. Okay. Myspare and ONNX. So Myspare has shipped with a built-in ONNX support. So as you can see from the figure, if you use Myspare to train a model, you can actually select to export a ONNX model if you want to do inference on CPU, GPU of your choosing. So in this example, after you have the ONNX model, you can use, for example, ONNX runtime to deploy your ONNX model for like CPU, GPU, or FPGA. Currently, we support 18 operators. It's very small now, but we plan to add more and more operators absolutely on the way. And also we have a small model zoo and in construction. So we'll be adding more and more support in the future. So MIR is another really interesting area for us. We've been quietly lurking and following the ONNX MIR development recently. So from our understanding, the ONNX MLIR provide a front end which can generate a ONNX dialect, which by the reference lowering can lower to the MLIR dialect and then to the LLVM dialect. So by having a ONNX front end, basically we can have ONNX model leverage the MLIR infrastructure. So what this means for Myspare is that if there's a customers or users have like new hardwares which came with LLVM support, they can actually have Myspare to export a ONNX model, and by the help of the ONNX MLR project to run the model on the new hardware, which will be a very exciting feature, I think. Another new area that we are really interested in is Onyx Training. So as just mentioned, with 1.7, we already have some tech preview of Onyx Training support, and Myspare community definitely we if there's like any experimental work that we can do to help either validate or try out with the Onyx Training model, we are definitely want to help out with that. Okay. So for Myspare itself, you can check out the code or just try with Docker. We have Docker images. So it's open governance, so feel free to, for example, if you are really interested in Myspare and ONNX support, you can initiate, suggest an ONNX working group in the community. You can join our Slack and also our mailing list. So in conclusion, we really like ONNX community, and we want to further collaborate. Okay, thank you.
Okay, thank you, Howard, very much. I appreciate you taking time. I know it's very late local your time.
Yeah,
so
no
thank
problem.
you. All right. So with that, I guess we have Emma Ning from Microsoft is up next. I'd like to see if you see the new screen share. So Emma. Emma, are you with us?
Hey guys.
Yeah, we can hear you now, Emma. Thank you.
Oh, okay, sorry. Okay. Good morning, everyone. This is Emma from Microsoft. I want to share our recent optimizations in Onyx Runtime to accelerate transformer inference on both CPU and GPU. Yeah, our team has been using cutting-edge NLP techniques to better understand user queries on web pages and other documents. So with transformer models, Bing has delivered the biggest quality improvements to search users. Next. As many of you know, the state-of-art transformer models has showed very promising results for NLP tasks. One of the most popular transformer model is BERT. Google originally released two versions, a 12-layer BERT and a 24-layer BERT. The problem here is both were pre-trained with up to hundreds of millions of parameters, which significantly increased computation load compared to the previous network architecture. Next. Yeah, let's see what Bing did with transformer model. Previously, Bing fine-tuned 12-layer BERT which improved the precision and the coverage a lot. But due to the significant computation required, inferencing 12-layer boot at high scale cannot meet the strict latency constraint. They first used knowledge distillation to condense the original model to a 3-layer boot. Then to optimize it further, Bing team re-implemented the entire model using TensorFlow, TensorRT, C++ APIs to take a full advantage of NVIDIA GPU architecture. These optimizations enable Bing team to meet the shipping criteria, but there is another problem. The current solution requires each model developer to re-implement the whole model with C++ library, which was very time-consuming. To democratize transformer inference and empower others to benefit from these advances, we further optimized Bing techniques and open sourced them in Onyx Runtime. Next. Okay, then how can we optimize BERT in Onyx Runtime? We identify some opportunities. The first, transformer models like BERT consist of a lot of elementary operators. Each one requires a read and write, which results in a huge amount of elementary computations. But one good thing is BERT is made up of multiple transformer cells. Actually, the high-level design of single transformer cell is simple. So you can see the design on the right. Our goal is to optimize the graph as simple as the design. We also noticed that current operators in Onyx Runtime haven't fully utilized hardware characteristics like CPU and Tensor Core. So on the other side, Onyx Runtime itself offers two major acceleration approaches in its architecture: graph optimization and execution providers. So execution provider is used to integrate different hardware accelerators. Each hardware accelerator has a specific optimized kernel for perf acceleration on that target hardware. So based on Onyx Runtime architectures, we optimized the BERT model by fusing key subgraphs into single kernels and implement related optimized kernel for both CPU execution provider and the GPU execution provider. This significantly reduced the memory copy between a huge amount of elementary computations. In Onyx Runtime, there are 3 levels of graph optimizations based on their complexity and functionality. Basic graph optimizations remove redundant nodes and redundant computation. Extended optimizations include layout optimizations, change the data layout to achieve higher performance. Yeah, next. As I said, our goal is to optimize the BERT graph as simple as the design. So in the design, there are 4 major paths. We fused a BERT graph following these 4 paths. Next. The first part includes 3 things: embedding, layer normalization, and attention task processing. We fused them into embed layer normalization. Next. The second one is self-attention. By fusing the self-attention as single kernel, we can get a fast memory access and increase the throughput of the model. Next. The native implementation of Genome activation used a bunch of elementary operators. We also merged them into a single kernel called Genome. Continue. The last one is skip layer normalization. Yeah, next. Here are all the graph optimizations we added into Onyx Runtime for BERT. You can see they cover both basic level and extended level, but the majority of them are at extended level. Here is all Onyx graph after optimization. So you can see it gets simplified a lot. According to optimized graph, we also implemented related kernels, making the most of hardware capabilities for both CPU and GPU. For example, on GPU, we leverage Tensor Core to take advantage of GPU architecture. On CPU side, we significantly increase the parallelization and fully leverage available CPU cores for Tensor for self-attention kernel. With all the optimizations, here are the latency and throughput numbers we got with Onyx Runtime. From the numbers on the left, with public BERT scored model, we could get 1.7 milliseconds for 12-layer BERT and 4 milliseconds for 24-layer BERT. On the right, with being a 3-layer BERT, we achieved 17 times performance speed up on CPU. And on GPU, even increasing the batch size from 4 to 64, we still observed more than 3 times performance speed up. We enable all those optimizations in Onyx Runtime by default. So you can get BERT perf acceleration with Onyx Runtime directly. Binting has updated their model inference solution with Onyx Runtime and found that Onyx Runtime was so much easier that the development time was cut from multiple days to a few hours. After Binting, Office team also adopted Onyx Runtime in their BERT model shipping. This is also 3-layer BERT. With Onyx Runtime, the P50 latency was reduced by 3 times compared to the original solution. And the development cost was also reduced significantly. Now, there are a variety of scenarios trying Onyx Runtime to accelerate their own BERT model. For example, Hugging Face. Hugging Face approached us to benchmark BERT perf with Onyx Runtime. Do you want to have a try? After you train a BERT model in a TensorFlow or PyTorch, there are only 2 steps to get BERT accelerations with Onyx Runtime. So the first step is to convert that model to Onyx using Onyx converters, then inference that model with Onyx Runtime. So it's pretty simple. We also provide a notebook you can follow to go through these steps. Lastly, I would like to share some data about Onyx Runtime adoption. Onyx Runtime has been integrated into both internal platforms like Windows and external platforms like Oracle. A variety of products like Bing Office, Azure Cognitive Services are powered by Onyx Runtime. Not only for transformable models, Onyx Runtime can also accelerate other kinds of machine learning models, including CNN, RN. We were observed up to 18 times performance improvement compared to the previous solution. Now, Onyx Runtime runs on millions of devices and is processing billions of requests in production every day. The adoption is keeping growing. Yeah, that's pretty much I have today. Thanks.
Thank you, Emma, for the presentation. This is very interesting. Thank you.
Thanks.
So with that, I think we're going to keep moving ahead. And so next we have Yaman to talk about the film. Let me switch to the presentation.
Can you hear me clearly?
Yeah,
Perfect.
I can hear you. I'm going to start the slideshow here. All right.
Thank you.
Over to you.
So good morning, good afternoon, good evening. I'm Yaman, and today I want to tell you about our project Fin and how we've been using ONNX to make it possible. Next slide, please. I'm a member of Xilinx Research Labs in Dublin, where our mission is to quantify the value proposition of Xilinx devices in machine learning. You may have heard of Xilinx, the inventor and the largest vendor of field programmable gate arrays, or FPGAs. Xilinx makes adaptable hardware solutions that balance the performance and efficiency of custom chips with the flexibility of programmable platforms. The project I'll be telling you about today is not an official Xilinx product, but a project from Xilinx Research Labs to explore custom neural network implementations on FPGAs. Next slide, please. So the Fin project is all about exploring what you can do by customizing both the algorithmic side of DNNs as well as the underlying hardware, which is made possible by the flexibility of FPGAs. We're specifically interested in what we call streaming data flow architectures on the hardware side. Next slide, please. In these architectures, we allocate compute resources to each layer according to their compute requirements and run all of them in parallel. Next, please. And by allocating these computational resources according to what that particular layer needs in proportion, next slide, please, we're able to achieve these architectures that lets us stream inputs through the custom hardware instead of doing the compute one layer at a time. Next, please. So this comes with great throughput and latency benefits. And next, please. On the algorithmic side, we're interested in quantized neural networks, or QNNs, with both weights and activations quantized down to a few bits. Let's say typically less than 4 bits, all the way down to a single bit. So this lets us keep more weights and activations on chip, which overcomes the external memory bandwidth bottlenecks and greatly increases performance. Next slide, please. So we've been exploring the combination of few-bit QNNs and streaming data flow architectures for the past few years, and these are a few highlights from some of our prototypes. So on simpler datasets like NIST, we can achieve inference performance in the millions of frames per second and sub-microsecond latency here. For instance, this is let's say, middle-class FPGA, the previous generation of our product line, which could do about 12 million frames per second with 310 nanosecond latency for a single image. Next, please. We can also scale this down to embedded or edge platforms and do object detection with real-time performance. Next, please. Or scale it up to data center class FPGAs and more complex topologies like ResNets to achieve thousands of frames per second with millisecond latency. So in general, we found QNNs and data flow on FPGAs to be a great combination, and we wanted to enable a larger community to explore these solutions. Next slide, please. If you can just go on next 4 times, I'll skip the animation. This is how Fin was reborn as an open source project. And what you see here is the summary of our mission statement. In essence, what we want to do is, through the power of open source and by tapping into existing open source ecosystems like ONNX, we want a wider community to be able to explore few-bit QNNs and their custom hardware deployments on FPGAs. And next slide, please. This diagram here gives you a quick overview of the Fin stack. At the top of the stack, we have Brevitas, our PyTorch library for training neural networks with quantized weights and activations. And being aware of the quantization at training time is essential to achieve high accuracy with these few-bit networks. Unfortunately, due to time constraints today, I won't be able to tell you much more about Brevitas, but please do check it out. It's also open source on GitHub, and we have a few examples of few-bit QNNs with training scripts and pre-trained models there. We have the Fin compiler in the middle. The Fin compiler is responsible for going from a Brevitas PyTorch graph down to an FPGA bit stream. It makes heavy use of ONNX, which I'll be talking about in the next few slides. And on the bottom, we have Pink platforms for deployment, which is another open source project from Xilinx Research Labs. The slide there. For a quick overview of the Fin compiler, in general, the Fin compiler is not unlike many of the other DNN compilers out there. We have a Python library of graph transformations, and we manipulate a graph representation via transformations step by step until we get to a bit file in our case. Perhaps most interesting for the ONNX community is our intermediate representation, Our intermediate representation is essentially ONNX with a few custom annotations and operators. And that is what all those graph transformations are operating on. Next, please. The particular backend target for our compiler is our own Vivado HLS or high-level synthesis library with templated data types and configurable parallelism. So you can explore different aspects and scale the performance up and down and explore different precisions. Next slide, please. I would like to highlight some of the things about how we're using ONNX inside Fin, since I said it is our intermediate representation. As I mentioned at the beginning, we're mostly interested in few bits, typically less than 4-bit, all the way down to 1-bit weights and activations. The existing standard data types in ONNX don't go below 8 bits. So what we did there to make this work for our use case is to hijack the quantization annotation field to annotate particular tensors with our own few-bit data types while using float32 as a container data type. Next, please. Another thing we do, which is probably not that exotic, is to use custom op types to represent non-standard ops we need at different levels of abstraction. So this can be all the way up to high-level abstract ops like im2call or a different data layout version of maxpool to actually implementation-specific op types. We also have Python wrappers of these layers to provide implementations for their execution for correctness and code generation. Next, please. We have a hybrid runtime that lets you mix and match different execution modes on different nodes. These include Microsoft's Onyx runtime for the standard Onyx ops, our own Vivado HLS C++ implementations for certain layer types, custom Python implementations, and even Verilog using PyVery later. I should stress at this point, this hybrid runtime is only for checking functional correctness while using the compiler. It's not for high-performance Onyx deployments just by itself. That is the output product of the compiler. Next slide, please. Continue with some more Fin Onyx highlights. As I was saying, we have a library of Python graph transformations, all operating on Onyx representations. This is quite similar to what the Onyx optimizers as part of the core Onyx repository already do, except it's all in Python. So we have transformations ranging from constant folding to convolution lowering and the shape inference, which is a mix of our own shape inference routines mixed with the standard Onyx shape inference. Next slide, please. Another thing we do to deal with few-bit tensors, which we need to do, is custom data layouts and packing. If you have 8 separate 1-bit values, you don't necessarily want to carry these around separately. You do want to pack them into as few bits as possible to decrease your memory footprint. So we do use these custom data layouts and the packing, unpacking utility algorithms to actually pack and unpack things like packing 8 separate 1-bit values into a single 8-bit value. And next, please. Last but not least, since Onyx is our intermediate representation, we use netrun for visual debugging and inspection of graphs at any intermediate stage, which has been hugely helpful for checking things like, we've transformed the graph a couple of times. Does the topology still look like what we expect it to do? We use the node attributes to carry lots of additional data. Is everything in place? Are the initializers all okay? And so on and so forth. Next slide, please. Finally, as I was mentioning, Fin has been reborn as an open source project from the ground up. We have a growing community spanning universities, makers, and other researchers, and we would love to have more users and collaborators. We've hugely benefited from ONNX's open ecosystem, as you've already seen in this presentation, and we are keen to find out how we can contribute back to the ONNX community in terms of few-bit quantized models and graph transformations and more. So if any of this sounds interesting, please do get in touch with me. And next slide. It's the end of my presentation. Thank you very much for this opportunity.
Thank you so much, Yaman, for your presentation. Let me stop share, move to the next. All right, Kishwa, can you hear me? Kishwa, you're next.
Hello, can you guys hear me?
Yeah, I can hear you now. Thank you.
Okay. Yeah. So hello, this is Kishwar. I'm going to give you an update of our project that where we use ONNX for genome analysis with nanopore sequencing. Next slide, please. So the way you do genome analysis is the first step is doing sequencing. So you collect a sample, you run it through a sequencing machine, and then you get a lot of short reads. Next slide, please. So from the reads, what you can do is you take all the reads, align them to each other, and then derive a de novo assembly. And this process is really expensive. And to do human population analysis, de novo assembly is essential. Next slide, please. And there's a lot of consortiums that are trying to do rapid de novo assembly of large genomes that require a way to do this assembly and an analysis of populations of large genomes rapidly, with not in terms of sequencing, but also in terms of computation. Next slide, please. Last year, we published a paper, and which has been accepted in Nature Biotech now, that showed that we can do efficient de novo assembly of human genomes using nanopore sequencing and the toolkit that we developed in-house in collaboration with Chan Zuckerberg Initiative. Next slide, please. So the whole pipeline looks like this. So you have a sequencing machine, then it goes through a base color, then an assembly and polishing step. And what we showed is you can do a population level human genome assembly within 9 days. Next slide, please. So the first is the Shafter assembler. This is the most expensive step of doing human genome analysis. So at this point, what you do is you take all the reads, you do a run length encoding, you align all of the reads that match to each other, and then try to derive a linear sequence that represents the underlying sequence of a genome. Can be human, can be microbial, or viral, or any other genomes that you just sequenced with a sequencing machine. Next slide, please. And then the assembly that we get from the Shafter assembler are highly erroneous due to the underlying errors you have from the nanopore sequencing. So we use a graph-based assembly polisher that takes the assembly and creates a partial order alignment graph. And this tool that we developed in-house can also output the state of the graphs in tensor format. Next slide, please. That can then take the graph states as tensor format as an input of the next tool, which is Helen, where we use a deep neural network that walks through the state of the graphs and then uses their deep neural network, recurrent neural network, and predicts a correct base and the number of times that base is repeated per position in the genome. And this is where we use the deep neural network, and this entire pipeline produces a high quality genome assembly. Next slide, please. So the base level accuracy, this is the base level accuracy we get from the assemblers. They look pretty good. They're almost 99% accurate. Most of the times, these are 4 assemblers that you can have that are available out there. And you can see that most of the assemblers generate almost similar base level accurate assemblies, but 99% is not very good in terms of doing sensitive analysis of gene expression or any kind of transcriptomic analysis. Next slide, please. So what we do with margin polish and Helen, if you use the polisher, then the quality of the assembly is much higher, and so you from 98 to 99.1, we go to 99.7, which is highly accurate, and we show that if we polish the genomes with this polisher, then we can do sensitive analysis. Next slide, please. In terms of runtime, Shasta is really fast. It can do a human genome assembly within 6 hours, and it costs only $70 compared to the other assemblers that are really expensive. Next slide, please. And for the polishing, you can see that the polisher is also really fast. The polisher that we developed compared to the compared to the state of the art. And here the trouble was that it was optimized for GPU, and we had a lot of users around the world who wanted to try this polisher on their CPU machine. And we recently, this year, we incorporated Onyx runtime, and this was in PyTorch. So what we do now, so every time you want to do CPU-based inference, you export the PyTorch model into Onyx and then run Onyx runtime, and we can easily parallelize the sessions, Onyx runtime sessions, and then collect all the predictions and stitch, and then generate the polished sequence. Next slide, please. And so far, what we have seen, these are all the numbers reported by various groups around the world who used our tool on their CPU machine. So what we see is that we got almost 8 to 10 times runtime improvement, and this is incredible because now we have heard that people are using this for microbial genomes, and we were able to do release microbial genomes, genome model due to this modification or incorporation of Onyx models into the pipeline. And we also are trying to see how much of an improvement we can get if we want to do a population level of CPU only, or probably with GPU only assembly and polishing pipeline with this framework. We haven't done that part yet. Yeah, so next slide, please. I think this is the end of the slides that I have. Yeah, we have a huge group, and we collaborate with a lot of people. And sure, if you think that this work is interesting and you want to know more about us, please let me know, ping me. And yeah, and thanks for all the work that you guys do. It's been really helpful from our viewpoint to have a platform where we can support CPU-based bioinformatics usage. Thank you. That's all for me.
Great. Thank you, Kishore, for that presentation. Yeah, we will have a Q&A session at the end of this presentation block. So hopefully we can have more discussion at that time. All right, so moving right on, let me switch to the next presentation. All right, let's see. We have Yongshin on.
Hi, Yongshin here. Can you hear me?
Yongshin, yep.
All right, cool. Thank you. Hello, everyone. I'm Yongshin. I'm from the Microsoft, the Azure Cognitive Service. I work in the OCR team. And for about over 1 year, we've been working with the Onyx Runtime team to use the Onyx Runtime to take our state-of-art OCR engine to production. So today is to share the journey. So next slide, please. So this is just a quick introduction about our product. The Microsoft Cognitive Service is a set of a cloud-based AI offering. So that includes things like speech, vision, language, so on and so forth. And for our team specifically, so we work on this READ API, which is state-of-art, the optical character recognition engine, commonly called as OCR. Right, so and this is a engine actually coming from the Microsoft research. Yeah, so it's really built from scratch using the deep learning. And the thing that unique about it compared to the more traditional OCR is that we actually internally call it one OCR. That means we just need use one OCR engine to deal with different kind of scenario. So for example, it can deal with the printed text, it can support recognition of handwritten text well, and then also from the sample on the right, right? So it actually works pretty well for the real world images, right? So no matter it's a product label that you capture using the mobile phone, or a quick snapshot that you take with on the slide, or the like receipt in different angle, so document in different angle, it all work pretty well. And feel free to search for cognitive service computer vision for more detail. Next slide, please. All right. So and I would like to talk about our journey to to Onyx. Before it's actually in late 2018. At that time we are using. So we are an engineering team. We've been working with the researchers, and then we taking the model that research give to us, and then there's a homebrew. The homegrown inference engine, right? So inference on that model. But as you know, the PyTorch is really getting popular at the time. So researchers still want to use the PyTorch to continue their research work. And then we do have this mismatch about the research and production. The other thing is around the performance challenge. Although our homebrew engine has the advantage of like knowing the model closely, so they try to optimize it. But the truth is that since we are not a team that really focus on the inference engine, right? So it start to lag behind. So in terms of the state art, inference technique. And our first try is that to see if the Cafe 2 can meet our requirement. But unfortunately, at some prototype, so in terms of performance gain, it's just not there. Next slide, please. Okay, so this is where we start to switch to the Onyx model, right? So because the one is that so now it's a modern framework both for research, training, and inference. And then this really allowed that so research start to use in the PyTorch, and then can use PyTorch to export the Onyx model to us, and then we can just use in the in this case, so some of their code will be in Python. Then we will actually convert so the all those Python code, and then also take the Onyx model they export, and then into our production C++ code. And then also because Onyx runtime is really optimized, right? So it actually work well for the service deployment because this is cloud service. And then we're also very lucky to have a close working relationship with Onyx runtime team to support this journey. Next slide, please. All right, so our porting experience is actually pretty straightforward. The read 2.0 version is a Windows-based cloud service. Because we did some initial work with the Cafe 2, we are able to use the Cafe 2 to export the model to Onyx. We do have some custom app, so that we use the C++ to implement that in Onyx. And then we use this to use Onyx API, to do the inference, and then after that just do the testing, so on the performance and on the service deployment. Next slide, please. Yeah, and we are actually very happy to see the performance gain that we are able to achieve. Originally, our goal is to achieve 3 times the latency improvement, but after using the Onyx runtime, we are actually able to overachieve it. So by to achieve 3.7. So that really helped to reduce our cloud costs. And not only that, we have been very happy with the reliability, and then also the the memory consumption of the Onyx runtime in our service environment. Next slide, please. All right, so after we shipped 2.0, we actually know that we want to switch from our Windows-based cloud service to Kubernetes, right? So because Kubernetes compared to the original Windows service that we have provides a better scalability, reliability. On the other hand, we also have a lot of customers after using our cloud service came to us to say they actually want to have Linux container so they can deploy our state-of-art OCR in their own network environment. So this is why that we start to doing the work porting from Windows to Linux. And because we use the Linux Onyx, and due to its cross-platform nature, really make this the journey to be easy. Frankly, actually, most of the code, most of the changes really on our own code. Yeah, so it's really not on the Onyx Inference code. And one of the good surprise, although it's not that unexpected, is that by switch to the Linux with Onyx runtime, we actually get better performance. Well, we are seeing about 1.2 times performance gain after switch to the Linux. And one thing actually I should mention in the very beginning is that so for the cost reason, all of our inference is CPU only. Yeah, so. And then the but even for the CPU, Onyx runtime is really yeah, so pretty optimized for our purpose. Next slide, please. All right, so and overall we are really happy with our Onyx journey, right? So just as a summary, right? So it really helped us to have a good pipeline from the research to production. There's no gap anymore in terms of model. And then for the runtime itself, yeah, so it's it's easy to develop, it's easy to deploy. We got the great performance as well, and then of course it worked well for the Kubernetes the deployment. And as a matter of fact, all of our new yeah, so research feature development now all centralized on Onyx and Onyx runtime. So we're definitely looking forward to keeping improving this step-out engine by using Onyx. Yeah, that's all from me. Thank you.
All right, thank you so much for that presentation. All right. So let me switch to the next one.
Hey, Thomas, is it?
Yeah, should I? Yeah. So
hey, hi.
you want to drive the presentation, or you want me to?
Sure, I will share my screen. I can share my screen.
All right.
Let me know if you can see my screen.
Yep, I can see it now.
Okay. Cool. So thank you, Thomas and Prashant, for giving us the opportunity to talk today. So I'm Shaunak Mitra. I'm the product manager for deep learning at MathWorks, and I'm with Ting Su, who is the development manager for deep learning. So today we'll be talking about Onyx with Matlab. In its essence, we'll be covering three main topics, starting with our investments in Onyx, how Matlab users use Onyx, and our current goals. So, so Matlab has a deep learning library. If people don't know, it's called Deep Learning Toolbox that can be used to design and train deep neural networks using automatic differentiation, custom training loops, and all those fancy stuff. So what we have seen in the recent past for about a year or so is that collaboration in the AI ecosystem has been greatly enhanced with the inception of Onyx. Onyx has open up communication channels for us to talk to frameworks that are used extensively by users in conjunction to deep learning toolbox. So Matlab can both read from Onyx and write into Onyx. In terms of our support for Onyx, like I mentioned, it can read from Onyx. It can read from Onyx in a couple of different ways. It can read an Onyx network, or it can take in Onyx layers. In about a minute's time, we'll see the subtle difference between these two APIs. If you have trained a deep learning model in Matlab, you can also export that into an Onyx model format via the Export Onyx Network API. We started supporting Onyx about a little over 2 years ago, and over the period of time, we have supported a lot of operators and layers for Onyx. That has in turn enabled us to be able to import the state-of-the-art pre-trained models from Onyx Model Zoo into Matlab that we can make available for our users to use so that they don't have to start from scratch. They can already use some reference models to start with. Now, the Onyx importer workflow is kind of an important part. For example, users choose any framework that they want to work with, convert their deep learning models into an Onyx model format. And one of the ways to import that into Matlab, wherein all the layers and operators are supported, is via import Onyx network. Once you import that, what you get is a Matlab neural network model, which is basically a native Matlab environment model. Now, this is an ideal scenario wherein once you import your Onyx model into Matlab, you can make use of all these downstream goodies that Matlab provides you with, like code generation, system integration, that we'll be going through when we talk about the use cases. This is also an ideal scenario. This is true for the deep learning models that are highly curated, where layers and operations are supported by all the frameworks. Now, what happens when not all the layers and operators are supported? This is something that we have seen being quite predominant among users, because they want to customize their deep learning networks. So in that case, what we allow is that we still would allow you to import Onyx models into Matlab. We'll allow importing of Onyx layers. And we'll introduce placeholder layers in place of the layers that we do not support. Now, if the user knows about the layer specs and the mathematics behind the layers, can author custom layer, and can also, after that, can also replace the placeholder layer with the custom layer. Once they do that, it's as good as a Matlab neural network model that can make use of all the downstream workflows, including code generation of custom layers. That is something that we are actively working on to support in the future, in the near future. Now, how Matlab users use Onyx. First, we'll talk about how Matlab users use Onyx for export to Onyx workflow. Users use Matlab for different parts of the deep learning workflow, as Matlab supports data access, data labeling, training, pre-processing, and deployment. So what we have usually seen typically is for users to start with something called as a labeling step, wherein they bring in their images or data into an app, which is an annotation tool. For example, in this case, what you're looking at is an image labeler annotation tool. You drop in the images here. Say you have hundreds of frames or images. You would label a couple of frames or images, and you would want to automate the entire process. The labeler app allows you to do that by defining region of interest, drawing bounding boxes, and once you're happy with the bounding boxes, you can automate the labeling process using the algorithms that we provide, or you can also write your custom algorithm. So this is a typical workflow that users use to quickly label their data set. So not only we provide labeling apps for not only images, but also for signals or LiDAR point cloud labeling for ADAS kind of applications, video labeling as well. Next up, users have used Matlab for decades for their engineering applications across various domains like audio, computer vision, controls, LiDAR, etc. So this is a strong part when users use Matlab for. Then comes the training part of the workflow, wherein users use a thing called as Deep Network Designer app. That is basically a point and click tool for you to drag and drop layers on a canvas real quick, connect them, edit the layer properties, and once you're done with that, you can import the data, inspect the data, and then define training parameters or hyperparameters and train all within the same app. So this app covers the entire end-to-end workflow. And once you're done with that, you can generate code, Matlab code for training that will be a command line way for you to do further custom stuff. So once you're done with the training, the users are typically exported to Onyx model format, wherein they use it with Onyx runtime for deployment purposes into FPGAs and other platforms. Now, this is the export to ONNX workflow. There's also an import from ONNX workflow. So users typically use Matlab as a platform for code generation, visualization, retraining the models with some of their custom data sets, and Simulink, which is also a flagship product of MathWorks for system integration. So we'll go over each of these things in a little bit of detail here. So this is the workflow that you have already seen. You have ONNX model, you import ONNX network into Matlab. What you get is a Matlab neural network model. You can take the code generation route, which is the #1 reason why people choose to come to Matlab after they have an ONNX model. That's how typically they use ONNX models with Matlab. In its essence, it supports you to create or generate, auto-generate C++ or CUDA code to target Intel CPUs or GPUs, NVIDIA GPUs, CPUs, and so on and so forth. One of the other reasons is also for visualization and debugging. It's mostly related to why a model is picking up an inference number. It's more regarding the explainability and interpretability of models. Our customers also bring in ONNX models into Matlab to analyze the network, to visualize the network and see what's the activations, what are the issues going on with the network. It's similar to what Netron does. And they can also retrain using automatic differentiation, custom training loop, or weight sharing. Now, the last point is kind of an important point, and it's something that we have been seeing quite a bit in the last few months or so. This is something in line with what Steven from IBM mentioned, that ONNX is being used for non-deep learning purposes as well. And this is something that we have seen as well. For example, if you were to build or simulate a highway lane following application, deep learning is a very small component of the perception module of that ADAS system. There are various other subsystems or subcomponents like vision detector, sensor fusion, lane following decision and control, vehicle dynamics, and so on and so forth. Now that needs to work as a system. So, deep learning in its essence will be a very, very small part of that system, small but essential part of that system. And that is what I've recently worked with a couple of customers to help them use some of the ONNX models to directly work with the Simulink platform for system integration. And the system integration with Simulink is essential and a very, very critical part of our workflows for reinforcement learning, automated driving, and control systems. Now, talking more about system integration, the integration of model-based design and AI is central to some of our users. For example, Denso 10, which is a huge automotive electronics manufacturer from Japan. They have used AI. And Simulink for complex vehicle control issues. So this is a typical user story that we get, and we cannot edit it. So it's kind of wordy, and I understand that. So what I'm doing is I'm trying to highlight the essential parts here. So what they did was they integrated AI model into the existing control systems, used the apps for quick network construction so that they can do rapid prototyping to see if a workflow works or it doesn't, and work together with Matlab and Simulink, working together with language of tech computing as well as model-based design approach to build a system together for an AI application. There is another user story from Airbus, but I'm going to skip it in the interest of time to discuss our current goals. So our current goals are threefold for ONNX. Firstly, we aspire and aim to import 90% of the models released on ONNX Model Zoo. That is something that we take very seriously, and we treat that as a benchmark that we can import the latest models shared on ONNX Model Zoo. We support for quantization and multi-platform code generation for imported ONNX model. Has always been a strong point for us over the last year and a half, and we would continue to support that so that our users keep engaging with us with ONNX and other code generation workflows, and also support export 90% of the deep learning models trained in MATLAB to ONNX. Now, this is 90% because there are some operator mismatches of the things we support versus the things ONNX doesn't support, and things like that, that we would want to keep on increasing and making sure that we support almost all the models that we train in MATLAB to ONNX, to make it an open ecosystem for people to collaborate and work in the AI ecosystem. And that was it for me. Thank you. If you have any questions, I'd be happy to take them.
Yeah, anyone have any questions for?
Can you guys hear me?
Could Shonak
sorry.
say a little bit more about the operator mismatches? Which specific operators?
Sorry, I was I couldn't hear your questions. Can you please repeat that question?
Could you say a little bit more about the operator mismatches? Which specific operators?
Yeah, I don't know if Ting is on the call. Ting or Sarah?
Yes, I'm here.
Yep.
So currently, most mismatched model actually operators are the operators that are involving change the number of dimensions, like a scatter or gather or something, which we, like Matlab doesn't really focus on supporting those models operators, and that's the direction that we are working on.
Thank you.
Yeah.
Does Matlab use its own inference engine?
Yes.
Yes, we do use our own inference engines via MATLAB coder and GPU coder that helps you target CC++ and CUDA codes. So yeah.
Thanks.
Yep.
All right, I think yeah, we can keep going. This is the end of the partner and end user story. So we can open up for the next 5-10 minutes for Q&A. So I guess you're all free to chime in and ask questions of any of the presenter if you have any questions up to this point.
Chin has a question in the chat.
Yeah, I'm replying by chat if that's okay.
Yeah, for the benefit of everyone, if you don't mind, yeah, just share that response so everyone can hear. I'm not sure if the chat is that the private chat or to everyone.
No, it was to everyone. Yeah.
Okay.
Thanks for the presentation. How does it work with the retrain after import to MATLAB model? Does the MATLAB adds training elements?
Yeah, so once you import the model into ONNX model into MATLAB, you can set your own training options. You can set your own hyperparameters like learning rates and batch size and other things, and can also add layers that our deep learning toolbox provides, and maybe do some transfer learning to it, and read and retrain the ONNX model on your custom data set that you might have labeled or pre-processed in MATLAB. So you can make use of that workflow once you have imported networks into MATLAB.
For those customer story you shared, are they using your own inference engine or other runtime?
So they are using our own inference engine. That's mainly for the importing workflow. For the export workflow, when users train in our ecosystem, they export it to Onyx Runtime for some of the targets that we don't support, for example, FPGAs. So those are the cases where people use low compute, low power DSPs. That's something that we don't support. So people use Onyx Runtime, or they go to TensorFlow and use TF Lite for those kind of workflows.
Okay, and the Onyx Runtime, you mean the Onyx Runtime developed by your team, right?
No. So Ting, can you take that?
What's the question again?
I mean,
so go ahead, Emma.
my question is, so he mentioned that the customer is using Onyx Runtime. I just want to make sure that the runtime is is developed by your company, or?
I believe when Sean said Onyx runtime, what he means is the Onyx runtime developed by Microsoft.
Okay.
So basically, in Mesos, we provide two directions. We provide the flexibility, allow our users to convert model like Matlab deep learning models to Onyx, and then we also allow them to bring Onyx model to Matlab, so they can do either way.
Okay, got it. So those models are classical machine learning models, right?
Mostly right now we focus on deep learning models. We are thinking about support like their classical machine learning models.
Got it, got it. Thank you.
Yeah.
By the way, I noticed that there are quite a few questions asked in the chat that have been responded but answered. But this Q&A section is open to everyone. So to ask any question of the presenter, from this morning on, including the city committee members.
How do we compare? Hi, this is Sriwadi. How do we compare PMML format with ONNX? Are we? Yeah, I'll leave it there. Can you hear me?
Yes, we did. So who the question? The question is for whom? Who will take on that?
Yeah, anybody can take on that. I'm trying to look for a comparison with the PMML.
Hello, this is Svetlana Levitan from IBM. Yes, I have worked on PMML for many years, and now I'm working with ONNX, and I'm working on a document comparing the two. So basically, PMML has very good support for traditional machine learning, but does not support deep learning. While ONNX does support deep learning pretty well and has support for traditional machine learning, at least in the for sklearn. But I believe there are many parts of PML which are not yet supported by ONNX. So we are considering creating a converter from PML to ONNX, but that would also require adding a few features into ONNX ML which are not there yet, which would correspond to PML features.
Thank you, Svetlana.
Does that answer your question, or?
Yeah, I'll wait for that comparison report. Thank
Okay.
you. And how big of a data sets have we tried in all these examples, or that comes to your mind that various companies have tried? The size of the data sets that were ever used in on ONNX.
You mean for inference?
Yeah, any operations on ONNX.
So yeah, so I can speak on behalf of MathWorks. We have worked with gigabytes and terabytes of data for image-based workflows that can be used via data stores that integrate well with ONNX at our side. We don't have a maximum size, yeah.
Yeah. For Microsoft, we use ONNX in a lot of large data set, and we have large model like BERT, large GPT-2 and others, and we use it on also gigabyte of data. Yeah.
Oh, wonderful. And so far, I understand it's a single machine implementations. Have we thought of clustering or?
Sorry, ONNX is standard, does not so it does not constrain single machine or single accelerator or multiple accelerators. So is that you're talking about ONNX or ONNX runtime?
The runtime.
Yeah.
Okay.
So it depends. Yeah.
Thank you.
Yeah.
All right. Any other questions for anyone else?
Actually, I have a question for Matlab team. Are you going to support Onyx Training?
Onyx Training. So that is something that we had briefly discussed about, but it's something that we are currently not focusing. Ting, you can correct me if I'm wrong here. So this is something that we haven't gotten much requests from the users yet. So, and it's very user driven. So, but this is something that is something that we're aware of, but it's something that we might not be actively working on. But Ting, you can add your comments here.
So we know that like the current focus of Onyx models are inference, but it doesn't prevent our users from doing training after models are imported into Matlab. So basically the users can add the training options like provide in Matlab to just add the training elements.
Right. Okay. And do you support PMML in any way?
We don't support a PML for deep learning models.
No, for traditional machine learning.
We hear some requests for supporting PML for classical machine learning models, but I don't think we support PML for now, but I can double check.
And you said you don't, do you export the Onyx ML for traditional machine learning?
You mean export the classical machine learning models to Onyx?
Yeah.
No, we are thinking about, we have those plans, but we don't support those export classical machine learning models to Onyx right now.
I see. Thank you so much.
Thank you.
All right. Any other questions? All right. So sounds good. I mean, looks like if you have
a general question.
Yeah, please do.
Before you close, what are your priorities that you're looking from the community contributors like us? I am new here.
Perhaps Prashant, Harry, and Joe from the steering committee, will you answer that question?
Yeah, I guess in the next section, each of the different SIGs and working groups is going to give an overview of the current work and the upcoming work. And so that's going to be the place where you can learn about the type of things that are going on and how you can best get involved. At the highest level, so the SIGs are going to be focused on specific areas of ONNX. In general, we encourage you to, join the different SIGs. You can participate in the steering committee meetings, which are open to everyone. You can, facilitate kind of a adoption and usage amongst your customers and in your products as well. So there are a number of ways that you can kind of contribute to the ONNX community.
Yeah, in fact, that's how the IBM team started to contribute to ONNX. We start to join the different groups and learn what they're working on and find some synergy, and then we start contributing. All right. Any other questions?
Sorry. Okay. This is Chin. I just have one sort of request because I heard conversation about ML and also who's going to support training. I'll put a link in the chat. I'd like to have people working on converters, or even you have any interest, providing your views on where you are in terms of ML support and also training. And we will look at the poll results later. Okay, thank you.
Yeah, thank you, Chin. That's a good idea. All right. So with that, I guess we've been going for almost 2 hours now. Maybe we should take a short 5 to 10 minutes break. All right. So that'll give us a chance to take a quick break.